All right. Welcome, everybody, to this first of its kind online lecture talk. This is a new territory for Space Society 20, as we are just beginning with discovering the streaming. But thankfully, technology has advanced so far that it is very easy to actually set up a stream. Yeah, Andy, I think you're getting feedback from the stream, so maybe you can close that window and we can continue. Thank you all for being here. So today we have our guest lecturer, Andy McGarry. He was the spacecraft systems engineer on the Ulysses mission, and thankfully he has agreed to give a talk about the operation of the Ulysses mission, and also have a bit of a feedback about the scientific results that the mission has delivered. So since he is the main lecturer, I will let him present himself and the talk that he's going to be giving. And just a heads up, Andy, you're still muted on Google Meet, so just unmute yourself before you want to introduce yourself. Oh, I think you're still muted, Andy. Maybe you should close the other windows and then you can restart the microphone on the stream. In the call, I mean. So yeah, sorry everybody. There's a little bit of technical difficulties, but this always happens when you try out something new, and hopefully we're going to resolve them within the next 1 or 2 minutes, so that you all can enjoy the talk. Oh well, yeah, I think Andy will rejoin. Yes.
Okay, I've rejoined.
Yes. Hey Andy, we can hear you now. So just restart the presentation and we'll be on our way.
And hopefully we won't hear myself echoing in a few seconds.
Yeah, well, with a lot of progress comes a lot of challenges to resolve. So hopefully we can do that.
Sorry, I forgot to restart the presentation. Okay.
All right. Great.
I think we have it. So just confirm that we have the front slide.
Yes, we do. We do.
Okay.
Okay, Andy. Great to have you here once again. Sorry for a bit of a hiccup, everybody, but we're back. And so, Andy, take it away with your talk.
Okay, thanks very much, Igor. So good evening, everyone. So I'm Andy McGarry, and I'm very pleased this evening to be talking to you all about a mission that I worked on many years ago called Ulysses. I'm very excited to be talking to you this evening because I believe we have a lot of students and enthusiasts listening. And I remember when I was a student at university and I started my first job as an operations engineer, my first thought was nobody taught me anything about this at university. And that's why I started giving lectures years ago, and I'm talking about Ulysses today, is to try and give a little bit back and explain to people what it means to be a spacecraft ops engineer and some of the experiences we have. And that's very important as your students. You'll be designing future missions. So it's actually very useful if you have operations experience to take back into the design loop. So yes, here we are. Here's a nice artistic overview of the spacecraft that I worked on for many years, studying the sun, called Ulysses. And at the time, I worked for a British company called Vega Space Systems, which is now Telespazio Vega UK. And Ulysses was a very long mission, as you can see, about 19 years. And I worked on most of those. I joined a little bit after the launch and saw it through until 2004 when I went on to other things. And currently, I'm actually unemployed, so that's why I'm putting a little advertisement about myself at the bottom. I'm available for new roles from March onwards. But at the moment, I'm enrolled with the International Space University for a course which is coming up in January and February. Okay, so quick outline for the talk. I'll begin by giving you an overview of the Ulysses mission. And at the end of that, there'll be a little pause. So I'm happy to take any initial questions that you might have if anything's not clear. Then I'd like to spend a good portion of the talk talking about our operations experience, the philosophy behind that, and the challenges that we faced. We can have another break before we talk about the science part of the mission. And again, ask some questions there if you like about the operations aspects. And then I'll finish up with a sort of a fairly brief overview of some of the main scientific results. As best I can, I'm an engineer, not a scientist, but I've got some nice highlights of some of the main things that were discovered by Ulysses many years ago. And at the end, we'll conclude, and there's a chance for any final questions that I can help you with. So let's begin with an overview of the Ulysses mission. So actually, Ulysses was initially conceived literally a year after Sputnik was the first idea. And of course, at that time, we'd only just got something in orbit. So although a scientist had a fantastic idea to do this mission over the poles of the sun, the technology just didn't exist at the time, of course. So it wasn't until the early 70s, after we'd started doing planetary swing by gravitational maneuvers, that people realized that a mission like Ulysses could be done. So we were initially, the design went on through the 70s. Initially, we were prepared for launch in 1983. Interestingly, Ulysses was originally conceived as two spacecraft, one from NASA and one from Europe, and they would have been actually going around the sun in opposite directions. But unfortunately, due to various delays and budget issues, the American spacecraft was cancelled. Fortunately, that still left us with one spacecraft. And again, really interesting design mention for you there. If you want to make sure your mission happens, maybe design it for two spacecraft. And if there's a cut, at least you've got one left over. So we were prepared for launch in 1986 and things were nearly ready to go. And then unfortunately, the Space Shuttle Challenger disaster happened in 1986 and all shuttle launches were put on hold. I'll get into later then when Ulysses eventually got launched. So the goal of the mission, nobody had ever looked at the poles of the sun before. So you have to imagine, if you compare it to our knowledge of Earth, imagine if you only knew about Earth from what you could see at the equator, then you'd really be missing out on a lot of information on how different the world is as you go towards the poles. And it's the same for the sun. The scientists just didn't know how the heliosphere was above latitudes of around 10, 20 degrees or so. And so this was the main goal of the mission, was to explore the sun with a view on the near polar orbit. Ulysses is the only spacecraft in this very unique orbit, and I'll be able to show you how that looks later. And the scientific aim, so it's literally creating a more three-dimensional model of the heliosphere than the rather limited view they had prior to this. And as is the case with many science missions, Ulysses was not the only one studying the sun. And so we coordinated our data. It's very important for scientists to have lots of different perspectives for their scientific observations. So we were coordinated with missions that were operating more closely to the sun, like SOHO. We have the Japanese spacecraft called Yoko. Cluster was a constellation of four European spacecraft orbiting in the magnetic tail of the Earth, and other US missions called ACE and WIND. And these were coordinated through collaborative science programs such as the Sun-Earth Connection, the International Living with a Star program, and the Interplanetary Network. So here's a little overview of the Ulysses spacecraft itself. So it's actually not that big. People have described it as about the size of a grand piano, or it would fit on a table. So it's sort of 3 by 2 meters in size, the main box construction of the spacecraft. And as you can see, there's a couple of main features that are immediately obvious. One is the high gain antenna for receiving commands and transmitting data back to Earth. And at the top of the picture, you'll see the radioisotope thermoelectric generator, the RTG, which was able to provide us with some power all the way out to the distance of Jupiter. And some other statistics. So the total spacecraft mass was about 370 kilograms, of which about 55 were the scientific payload. So actually quite a high payload ratio. And of that also included about 33 kilograms of hydrazine propellant for the thrusters that we had on board for various operations. So looking at the spacecraft, you have to imagine that the whole thing is spinning around at about 5 revolutions per minute, 5 RPM, slowly rotating. And that helped with the stabilization of the spacecraft, kept it pointing towards Earth so it could be transmitting its data and along the axis of the antenna. Normal operations were planned to be using antennas to track the spacecraft live for about 10 hours per day. And the goal of the mission was to get, I think it was around originally 95% data returns. So trying to get all of the data back. And I think actually in the end, we achieved 97%. So we actually managed to get even a little bit more than that. So some interesting facts and figures about Ulysses. So it was launched on the space shuttle and filling the cargo bay of the space shuttle. So the spacecraft was actually quite a small part of that. And below, it was mounted on top of two massive upper stages, the inertial upper stage and the payload assist module. And when these things were fired, they actually accelerated Ulysses to the greatest velocity ever achieved by a man-made object at the time, more than 41 kilometers per second. And this is why we were able to get out to Jupiter so quickly. The final orbit that we ended up in after doing our swing by around Jupiter is actually got an orbit period of about 6.2 years. And actually, we orbited as between the distances of Jupiter and roughly Mars. So we never got any closer to the sun than the distance of the Mars orbit, roughly. And that whole orbital plane was inclined at about 80 degrees to the ecliptic plane, so a near polar orbit. At our maximum distance from the sun, or aphelion, we were about 810 kilometers away, or 5.4 astronomical units. And the minimum distance was around 200 million kilometers at perihelion, or 1.3 astronomical units. By the end of the mission in 2009, Ulysses had traveled an incredible 8.6 thousand million kilometers, or 57.65 astronomical units. And somebody did a calculation, and that's an average of around 56,000 kilometers per hour. Another amazing fact is the speed of the solar wind that we measured. It's actually moving very quickly away from the sun at speeds of between 350 and 750 kilometers per second. And again, I've got some nice plots at the end of the presentation to show you how that looks. And Ulysses was a very nicely designed spacecraft. I actually read somewhere that the New Horizons mission that went to Pluto a few years ago actually looks quite similar to Ulysses. You can see a lot of similarities in the design. Unfortunately for Ulysses, New Horizons then took away the Ulysses speed record because it had to go even further away. And then a couple of years ago, another solar probe from NASA called the Parker Solar Probe, it's actually even gone even faster. So unfortunately, that's one record that Ulysses no longer holds. So let's talk a bit more about the mission. So here we have a nice picture of how Ulysses looked in the cargo bay of the space shuttle prior to being released from the space shuttle. And we were launched on the 6th of October, 1990. So last year, I gave a series of talks about Ulysses and wrote an article about the spacecraft because I wanted to celebrate the fact that it was 30 years already since the launch of this mission on STS-41 Discovery. And here's an artist's impression of how we looked as we were going around Jupiter. So the mission itself, we always talk in spacecraft terms about the mission. So the prime mission was designed to take just under 5 years, from October 1990 and finishing in September 1995. I joined the mission because we had a peak of activity around the Jupiter flyby, and that took place on the 8th of February 1992. A very intense period of operations as we were trying to also take observations as we swung around the planet and test the instruments. And here's another nice view of how that orbit looks after we had swung past Jupiter and rotated the orbit. Luckily for us, the mission went so well that we were able to secure some mission extensions. So the first extension took us again over the poles of the sun, and that went from 1995 to 2000, the end of 2001. And then we had a further extension from 2002 to 2004, the second extension. And here we can see how the mission was looking at the end of that period in October 2004, when and this was just after I had left the mission. So at that stage, they were looking to extend the mission even further and just operate the spacecraft as long as they could, and continue to get science. And that finally the mission was extended a final time until from April 2008. And they had no idea how long the spacecraft would last, but actually in the end they continued to operate for almost another year. And if we look at the orbit of the spacecraft, this picture of the orbit, there's some nice things to observe as well. So if we see at Jupiter distance, we can see on the right of the picture with a little icon of the spacecraft. So here we are at October 2004. So it actually takes over 2 years to get to the point where we start the south polar pass. We call this the slow latitude scan. So this is almost 2 years duration to go this far. But then very quickly, we go from the beginning of the South Polar Pass all the way through to the North Polar Pass in 1 year. And that's obviously due to the orbital dynamics. So that hopefully gives you an impression of the way the spacecraft is moving. So Ulysses was a fantastic early example of how successful international collaboration can be. The whole mission was founded on a memorandum of understanding, or MOU, between ESA and NASA. And through all the tough times that Ulysses had through the course of its evolution, that MOU really kept things together, and the commitment that the two international agencies had together really kept it going through the tough times when a spacecraft was cancelled, the shuttle disaster happened and it had to be hibernated and things like this. People, the scientists and the planners kept it going because of this MOU. So really interesting point. So how do we split the contributions of the different agencies? So we split it down the middle. So ESA had a roughly 50% contribution. And from Europe, we were taking care of the spacecraft design. The spacecraft was designed and integrated by Dornier Systems, which is now part of Airbus. So they did the design, the construction, and the integration of all the experiments. European scientists and institutions provided 50% of the science instruments themselves. And luckily for me and my colleagues, they also provided the spacecraft operations team. And from NASA, their contributions were the shuttle launch to get us into low Earth orbit, and then the upper stages to get us into on our way to Jupiter. The RTG power source being a radioactive power source, of course, that had to come from the USA. America also provided 50% of the science payload. And then the other part of this that's happening, and I'll talk about this in more detail shortly, is the very important deep space network antennas, which enabled us to communicate with the spacecraft, to command it and get the telemetry back. And they also provided the facilities for ourselves in the spacecraft team to be co-located with our NASA colleagues at JPL, and that also was very, very useful in helping facilitate the way that we operated the mission together. The next slide, I'm going to show an animation of the orbit. So you'll see various color-coded lines, and Ulysses is in purple, so hopefully you can see that moving on your display when I show it. Here we go. So you can see Ulysses moving out to Jupiter, the sharp turn as we're getting our orbit rotated at 80 degrees to the ecliptic. And then as you can see, we just continue in that orbit forever. So even though Ulysses is now switched off, the cold, dead spacecraft is still orbiting the sun in this same trajectory. And also you can see the orbits of Earth and Jupiter for reference. And we've got a couple of or 3 other orbits marked there, which I'll talk about a bit later, of comets, actually. So these are 3 different comets that you can see superimposed in this animation. So why were we launched? Of course, we have a scientific mission, so we need to talk about the scientific payload. And here you see a outline of the spacecraft showing the main payload elements. And Ulysses had a suite of 9 different instruments, so a lot of cooperation was needed on this mission, because you've got 9 institutions with their precious instrument that they're the only ones that are worried about. So there needed to be strong coordination and management of the science and the science teams, and they needed to interact and collaborate with us on the operations side. So a lot of interactions, a lot of interfaces and collaboration for all these different teams with all their different needs. We had a range of instruments which were designed, of course, to study the sun and increase our heliospheric knowledge. So these focus on areas like radio science. So we had various types of radio antenna on the spacecraft. We were looking also at various electromagnetic fields. We were looking for dust particles and electromagnetic waves as well. So quite a diverse set of instruments. But unfortunately for us, we didn't have a camera. So of course, science missions get a lot of publicity if they have visual images. So we had missions like SOHO, which takes amazing pictures of the sun and its corona. And the original Ulysses mission with the two spacecraft, the American spacecraft would have had a camera. But when that one was canceled, then we lost our camera. So that was unfortunate. So I'm asking a question here: where can I see Ulysses? So I don't literally mean where can you see it, because it's orbiting too far away for us to view. But for those of us, I think most people here are watching from the Netherlands. So if you ever have a chance to go to the wonderful Space Museum in Noordwijk next to ESTEC, and you look up at the ceiling, you will see a full-size model of the Ulysses spacecraft. So I was very surprised the first time I went there and saw this hanging above, and it really helped me to bring back the memories of working on this mission. And if you look in the back of the wall in the background, you'll see a watch there, but don't worry, that watch is not to scale. So it is actually a giant watch from a sponsor, I think. But as I said earlier, so the Ulysses spacecraft is about 3 by 3 meters by 2 meters in size. So it's quite a decent sized spacecraft hanging above your head. So that was the first part of the talk about the mission overview. So I just wanted to pause and check that everybody can hear me, and if there's any initial questions.
So, yeah, hey, thanks, Andy. It was a nice first part. I think we actually already have a first question that we can ask you. So we have a question from your coworker from Serco, and he is asking, how did you get to be the part of the Project Ulysses? So maybe you're getting there already, but if you wanted to answer that question, you can go ahead and do it now.
Sure. Well, I've often started this talk by saying I always remember the quickest decision I ever made in my life. It was when my boss walked into the office I was working and said, "Andy, would you like to go to California for 4 months to work on Ulysses?" And about 10 nanoseconds later, I said yes. And so the whole process started. But basically, I'd come out of university with a degree in aeronautics and astronautics. And I initially I'd started working with jet engines, gas turbine engines, and I saw a job ad for spacecraft operations engineers and applied for it. And even though I'd only done really one course at university, they saw the potential in me. I got the job and started working on operations engineering. And as we were a consultancy, we had often new clients, new projects coming up, and they were looking for someone who had the knowledge and was flexible enough to just go off to California for 4 months for a short time period. And well, as it turned out for me, it turned out to be nearly 13 years.
Yeah, thank you. And I think we have another question that we can take right now, because I think this was relevant to what you said.
Okay.
I think Alexander has a question that says, how do they put that giant structure in space? So I imagine that refers to the launch. I think you mentioned something about it, so maybe you can go over it again to answer the question.
How did we get the spacecraft into space? Is that the
Yes, how
question?
did they launch it there?
Yeah, we were launched inside the U.S. space shuttle. So I showed a picture earlier of the stack, as it's called, the spacecraft with the upper stages, and that's sitting inside the space shuttle cargo bay. I believe it pretty much filled the cargo bay, and then of course before launch the covers are closed, so you don't see that. But hopefully everybody's seen the pictures of the space shuttle launches, and we were inside that. So that was obviously a key way to get the contribution from NASA was absolutely key to getting us into the right orbit with the shuttle and then the upper stages.
Yeah, thanks. I think we'll take the other questions at other question points in time. So let's just continue with the talk for now.
Fantastic. Okay. So are you seeing the Ulysses operations screen again?
Yes.
Yeah, great. Okay. So I've mentioned a few times, so that I was working as a spacecraft operations engineer. And as I said at university, I'd never heard of this as a job. I didn't know what it meant. Um, so here you see a picture of the globe, and I've superimposed some pictures of the various antenna sites that we used in the NASA's Deep Space Network. And these were necessary in order to get our commands up to the spacecraft, check that they had worked, and then receive the telemetry, the science data back from the spacecraft again. So these were absolutely key in a key part of the whole mission. And I really want to make sure people realize this, because we all talk about the spacecraft and how amazing they are, but we need to also consider it's a system. We have all these different working parts, and a lot of that is mundane stuff. It's cables, it's radio transmissions, but without these, of course, we're not going to get our data. So these things all need to work in concert for the mission to be a success. Another thing to notice here about the Deep Space Network, across the bottom are the photographs of the three different sites in Goldstone in California, Madrid in Spain, and Canberra in Australia. So they're roughly spaced equidistant around the world, and you've got two sites in the northern hemisphere and one in the south. So that gives a lot of flexibility in the views that they can have of the various missions that they support. Okay, so operations philosophy. So when people are operating a mission, they need to think about how are they going to operate it? What is the particular nuances of this mission? What will it need in order to achieve its mission goals? So I'll try to touch on a few points here that were key for Ulysses. So as I mentioned earlier, it was actually really useful that the spacecraft operations team from Europe was co-located with their NASA colleagues. And then NASA provided everyone from the spacecraft controllers, so the guys who are actually sitting on the console, hitting the key to send the command to the spacecraft. Those were NASA, and then the rest of the planning and preparing the commands, that was down to the European team. So we were co-located, so that meant every day we could meet, we could check how things were going. We're obviously co-located. If we hadn't been, it would have been really difficult with the different time zones. So it really was important that we were in the same place. And remember, this was back in the 90s, so the internet was literally just starting. I mean, we started a lot of the work that we did was by fax machine. So I mean, things were a lot more primitive than they are now. So it was really absolutely important that we were located in the same place. So the way the Ulysses mission was planned was we had to have a track, so a view from an antenna every day using the Deep Space Network. And we had different types of operations. So we had routine operations. So these were the typical 10-hour a day tracks that we would have. And these were what would happen unless we had some kind of encounter or science campaign, or if you had an anomaly, then you would either plan if you knew they were coming, or if you had an anomaly, you would request emergency full coverage, so 24-hour views a day. And then later on in the mission, when the science return was lower or Ulysses had lower priority and we had reduced operations, then the tracks, we could only get maybe 5 hours a day of tracking that. It impacts on the mission return as well. So we were tracking the mission live. So you're getting the real-time science data as it's happening from the spacecraft. And then between the passes, we would be recording that data, that scientific data, so that we would have the full 24 hours, or pretty much the full 24 hours of scientific data. And then on the next pass, we would play back the data that we had recorded. So this was literally the daily cycle that Ulysses depended on, was the real-time pass. Then we'd have a gap in coverage, and then the next day you'd have another pass. You'd be playing back the data from the non-live period before, and hopefully getting that all back. Again, taking real-time data, et cetera, et cetera. And that was just an endless cycle that we had. And the mission was originally conceived for about 5 years, and that was with the full science payload. We actually managed to string things out until May 2002, and that was the first time that we had to do what we called payload power sharing. So, in other words, when we couldn't have all the science instruments on at the whole time, and that was really important. So instead of just getting 5 years of full science, we got actually in the end almost 12, which is really uh, quite an achievement. So let's talk about those routine operations. So the routine ops are driven by the spacecraft tasks that we had to command and plan, and this antenna tracking schedule that I mentioned. So when can we actually communicate with the spacecraft? And a key thing here, and this again is going back to designing missions. It may sound amazing now, but we were literally using 70s technology. So we could only store on board the spacecraft 40 uh, TT commands, I call them here, time tagged commands. So these are commands you can store on board. You can specify a time when you want them to be executed, and then they will happen, for instance, out of pass or at specific times when you want things to happen. But we could only use 40 of those. So we could literally only do the routine operations for about 2.5 days, maybe 3 days at most. And in reality, that means that you're pretty much working in near real time operations. So, yeah, there's not much capacity for any errors, mistakes, missed passes. You really don't have much time to recover. So the routine operations, so the operations we were going to do were greatly influenced by the science that we wanted to do. And the mission science goals were discussed and agreed at meetings that took place roughly twice a year. And this is when the science teams and the operations team would get together and we would discuss, of course, how the mission is doing and looking forward to seeing what we needed to plan for the next phases. The real time science inputs were provided to us, the members of the flight control team, as they were needed. So sometimes we would come across opportunistic science opportunities, things that weren't known in advance. So an example of this would be in the, I think it was the 90s, when a comet broke up and crashed into Jupiter. We planned some extra science in case we could hear some radio signals being generated by that. So that was additional real-time science input. We had to see if we could fit it into the schedule and plan and work closely with the scientists to achieve that. Link budgets. So hopefully you've all studied link budgets. So looking at the RF signals and making sure you have enough antenna power and focus to get your signals to where they need to go. And if you imagine Ulysses in its orbit, it needs to point back at Earth, and the Earth and the spacecraft are moving relative to each other. So pretty much for much of the mission, every 3 days, we needed to do what we called an Earth pointing maneuver, where we would just nudge the spacecraft rotational axis slightly to keep it pointing at Earth. So we'd point it ahead of Earth, and then the Earth would go past us again, and then we'd repeat that cycle. So roughly every 3 days, we also needed to do an Earth pointing maneuver. If we didn't do that, if there was a problem with the signals or the commands, we would very quickly lose contact with the spacecraft. And another thing, this was completely new for me, and again, it's something which is really interesting. If you've worked on a spacecraft mission in near Earth orbit or geostationary orbit, you might get a fraction of a second delay or maybe 1 or 2 seconds delay at geo distance. We were working in deep space. We were all the way out to Jupiter orbital distance. And at the extreme range that we had transmission time, a one-way light time for commands of up to 53 minutes. So literally you could send a command, go and have lunch, come back, and about an hour and a half later, see what happened. But this has implications because if you need to wait on the result of something or you have to confirm something before you proceed with the next step, it can mean that some operations take an awful long time to complete. So that was a big influence on any operations that we had to plan. And then we also had the final operations. So as the mission went on through its various extensions, if we look at the period from 2004 onwards, which was actually, I'd left the mission, but the plan was that we would just try and continue operating as long as we could and as long as there was sufficient science. Because of course, running these missions costs money, and there are lots of other missions to consider. So Ulysses had to be compared, its science return had to be compared against the others, and it had to be justified that the mission would be extended. Luckily for us, we had a pretty robust and reliable spacecraft. So this is one thing to say for quite a simple design with simple electronics, simple computers. So we didn't, in the end, we could say we didn't have that many anomalies. We did have our backup onboard computer or central terminal unit, CTU2. We found when we did that after the Jupiter swing by that actually we had a data corruption. So this was our backup computer, and we just had to hope that the prime one wouldn't fail, because if we had to switch to this backup, there would have been a lot of misleading data from the spacecraft. We did have a slight plume impingement from one of the 4 axial thrusters. So the analysis of this anomaly actually discovered that the plume from the thruster was actually impinging against one of the instruments on the spacecraft. And this is something that hadn't been fully anticipated in the modeling and design and testing of the spacecraft. So we had to be aware of this when we were planning these maneuvers, because that thruster would actually have a slightly different vector compared to the others. So that was something we had to be aware of in planning future ops. We also had a very serious anomaly that we had, was called the nutation anomaly, and I can give you a bit more information about that later, but that's basically a very severe wobbling of the spacecraft. And after 12 years of service, we did lose one of our transmitters, our TWTA, or traveling wave tube amplifier, failed. So these are very delicate devices. They are vacuum tubes. These are what amplify the signals from the spacecraft and enable them to be transmitted. So again, when we talk about operations philosophy at the time, the philosophy was don't switch it on, don't switch it off. Just leave it on as much as possible. Each time you switch it off, there's a risk it won't switch on again due to the delicacy of these components. But we managed to keep that first TWTA operating for 12 years. Another contributing factor, of course, was we needed fuel in order to keep doing these maneuvers. And it was determined in 2004 that hopefully we had at least enough fuel for operations through 2008. And the power was also a big factor. How much power could we get from this RTG? And again, the predictions were that we could run some of the payload at least through 2008. The other thing that was a big factor here was, as the power source decreased, we had less power available to keep the spacecraft warm. So at the furthest distance of the orbit, we were struggling to keep the spacecraft warm enough and avoid problems like freezing the fuel. And we were really pushing the thermal limits. So I mentioned this nutation anomaly. So this first occurred in 1990, shortly after launch, when we deployed a boom at the rear of the spacecraft, the axial boom. So this is one of the radio antennas. And it was later determined, after much analysis, that this very severe wobbling of the spacecraft was caused because this 7.5-meter long boom was being warmed up by the sun at close range. It was warm enough to actually make this thing flex. And because this was flexing, it actually was rattling back and forth between the rollers that it was deployed from. And this going back and forth and hitting these rollers was enough to actually make the whole spacecraft wobble slightly as it then spun around. We did have some passive nutation dampers on board, but it was determined that these things must have been underperforming. And again, to acknowledge the designers, these things are extremely difficult to design on Earth and test, because of course we're testing them under conditions with gravity, and in space they don't have that. So nutation dampers are a very difficult thing to design, and in this case, they couldn't provide enough damping. We figured out that there was a nutation forcing function, and unsurprisingly, that's a function of the angle of the spacecraft to the sun. So how much sun is radiating on the boom that's sticking out the back. And it's also proportional to the inverse of the distance from the sun squared. And that meant, of course, as we moved away from the sun, the problem would go away. So we knew this would be coming back when we came back towards the sun, and we successfully controlled this in the first period of polar passes in 94 to 95 to less than 0.7 degrees. And just to put that in perspective, at the beginning, the spacecraft was wobbling up to, I think it was 5 or 6 degrees half cone. So it was really a severe wobble. And because we were returning over the poles of the sun on each orbit, this was then going to return in 2001 to 2001 and 2007 to 8. So to help you visualize how this would have looked, this is a little sketch of how the spacecraft might have looked if we had severe nutation happening. So in the center, you can see the spacecraft body. We see various antennas. So Ulysses also had some wire antennas deployed in this direction. And to give you an idea of the scale, these were about, I think, over 70 meters across, which is about the length of a jumbo jet aircraft. And then at the back below here, we see the axial boom, which was the one that was causing the problem in the first half, in the first case. And then in red, we see a sort of a rosette figure being traced. So this is the path of the antenna axis, or where the data is going. And you can imagine if the spacecraft starts wobbling and you're trying to point at the Earth, it won't be very long before you have big problems like losing the data partially or completely, because you're literally spinning around the Earth and where it is. And also with this spinning and wobbling, it's also playing havoc with the scientific measurements. The instruments are designed to be taken on a spinning platform that is very stable, and then suddenly it's got this wobble. So all sorts of problems if we had mutation, and that's why we had to do a lot of work to control this. For me, again, going back to this point about the importance of other parts of the system, I really realized how important the ground segment was in a mission like Ulysses. And essentially, for me, I think it's fair to say that in deep space operations, the ground segment also becomes a subsystem, as in others on the spacecraft, like the thermal and the structures and the radio frequency subsystem. It's another subsystem you have to consider when you're planning anything. And what were the reasons for this? So the deep space network we were using is, of course, a shared resource. So there are literally dozens of missions all fighting to get time to use these resources to communicate with their spacecraft. So all the time, it was a continuous effort to literally negotiate time from the deep space network. And we had colleagues who did this for us. We were told this was somewhat like playing a poker game, putting in your bids, hoping that you get them, and having to be firm and know when to really push things and stay strong and fight for what you needed. So again, these were sort of other people who were sort of the unsung heroes, making sure we had enough antenna time to do the mission. And as the Ulysses mission went on, during its extended missions, because it's not a prime mission anymore, it gets lower priority, so it's harder to get the time, especially when you keep getting new missions launched and they have new scientific campaigns. Another factor is that the DSN, it's a huge, massive, complex system. It's very reliable. I mean, it really performs amazingly, but it's continually being modified. So for instance, we had some impacts when some system upgrades were made, and we didn't realize that they'd have an effect on certain operations that we needed to do. And we also had, of course, problems. So systems aren't 100% reliable. So sometimes there'd be failures. So an example here I give is in June 1993, a main bearing of an antenna called DSS 61, Deep Space Station 61. So this is a 34-meter diameter antenna in Madrid. One of the main bearings failed, so the antenna is completely broken. So massive repairs that would take weeks to take place. But we managed, with our colleagues, to find a network that was used by the German space agency at GSOC in southern Germany. They had a 30-meter antenna at Weilheim, and we, for instance, were able to use that to help patch the gaps in the coverage that we needed. So again, all of this is less glamorous work, but it certainly makes an impact on the science return. So I'd also like to talk a little bit about the evolution of mission risk. So in spacecraft operations, we always like to say that if you go into a control room, people often remark how quiet it is. And we always say, well, if it's quiet, that means we're doing our job. We don't want to have people running around and panicking. So we're always planning ahead. We're always managing the mission risk. That's a very important thing to keep an eye on the whole time that you're working on a spacecraft mission. For Ulysses, one of the major contributing factors to this was the power that we had. So here's a plot showing the evolution of the power supply, how much power we are literally getting from this nuclear power source. On the left, you'll see the power in watts. So we were literally getting, I think it was 286 watts at the beginning of launch. So that is literally a couple of light bulbs. So not very much power to run the spacecraft. And as you can see over the years, this very quickly diminishes. Um, so at the beginning of the mission, so the first edition I've shown here in light yellow. So this is the prime period of the mission. So during this phase, we had enough power to run all the payload. We had full science complement on. We had things we say hot redundancy. So if a unit failed, we could enable the automatic switch over to another one. We didn't have to worry about that. We could just have the other one come on automatically. The power and thermal margins were good, so we weren't operating in very difficult regions of those. So speaking, especially compared to the rest of the mission, operations were pretty flexible, and it turns out we're pretty low risk and pretty stable. So here I've put the red line showing the prime mission power requirement. So this was something that was defined in the planning stages. And the idea was that at this stage, this would mark the end of the prime mission, because this is when they predicted you would be able to run the full instrument complement. So the next phase we managed, as I said earlier, to continue operating the full science payload for quite a long period of time. But we had to do this in a clever way. We had to share the power in the platform. So all the other units that are not the payload themselves, the platform, the bus of the spacecraft. So we had to be a bit smarter about how we operated these in order to give as much power as possible to the science payload. We had some units that we had to operate in cold redundancy. So if the prime unit failed, we would have to, we ran the risk of losing some data because we would have to switch on the replacement unit from scratch. And that could mean, for instance, an interruption in normal operations or a loss of data. We were now operating in reduced margins, so we were starting to get closer to our power and thermal limits that are very important when you're doing spacecraft operations. So the operations were becoming much more conservative during this period. They need a lot more careful planning and implementation. And then in the final stages of the mission, as you can see, I'm getting into the sort of red zone here as we get towards the end of the mission. So here you have to accept more risk. So the science and the platform, the payload and the platform are now sharing the power, because there's just simply not enough to go around, and there's a certain amount you need to operate the spacecraft. We had to also operate at minimal redundancy, so really reducing our options if things failed. We were working with zero margins, so we were working right up to the limits of temperature, so things were getting cold, or we were operating at the absolute minimum power levels. So operations now were much more complex, and now we were really having to manage the risk that we were taking on board in operating a spacecraft. So as you can see, as you go through the mission, and this is a very long mission, you're seeing 19 years here, you have to accept increasing risk, and the operations are going to get more complex. So what are some of the trade-offs that we had to make when we were planning the different mission extensions? So during the prime mission, the first 5 years of the mission, as I said, we had plenty of power, so we could have all the science operating and all the platform units that we needed. On the thermal subsystem, we had good margins, so the temperature tended to be above the operating limits, so working the ideal temperature range for units. We had some hot redundancy available, so if some units, if they failed, they would automatically switch over to the backup unit. With the data return, we could be quite conservative, so we were getting nice long tracks. We could sometimes we had chances to replay the data back, the recorded data, so we were really getting good data return. Commanding actually in those days could be done whenever we wanted during a track. Later on, because of the way the commanding operates and it actually uses extra power, we weren't able to do that. The nutation control, so for that first orbit, we were able to control the nutation 24 hours a day, and we weren't able to do that in some of the later orbits. And then I've mentioned an anomaly at the bottom called DNEL, disconnect non-essential loads. So this is an automatic safing mode of the spacecraft where it would switch itself off and go into a basic configuration. And if this happened in the early stages of the mission, we would be able to do quite a slow, cautious recovery and really understand what went wrong with the spacecraft. So, what were the changes as we extended the missions in these different aspects of trade offs that we needed to consider? So, on the power side, then obviously I've mentioned the power sharing we had to do. So we had to start by sharing the power allocated to different units in the platform, and eventually we had to reduce some of the science that was operating. So we had to identify a core science payload, and then the discretionary payload were items that we would take turns switching on and off and balancing with the remaining power that we had. As the mission continued, then, of course, the temperatures dropped at the further points of the orbit, and we were operating on very low margins with the temperatures at the what we call non-operating limits, so the absolute minimums that we really wanted to operate without risking damage. On the redundancy, automatic switchover side, so we had to accept the fact that some units would automatically switch over if they failed, so that was something also we had to accept that risk. With data return, so because sometimes we were getting less tracking time, we would have to take a risk of playing back the data at higher speeds. So the benefit of that is you get the data back more quickly, but the problem is that if you have any data outage, then you lose a lot of data. So that was the risk that we had to take on board in the later stages of the mission. Commanding, so yeah, later on in the mission, we had very restricted commanding periods because that took more power from the platform. So if we had any complicated operations, those had to be very carefully planned. And then imagine with the one-way light times and how long it takes to receive confirmations, that really makes it quite tricky to plan operations. And then the nutation control, even in the last orbit that we've seen here, we could only really actively control the nutation using an onboard system for about 10 hours a day and hope that that would be enough to keep the spacecraft safe. And the last point in the trade-offs that we had to accept was that this safing mode, we would have to do a much quicker recovery and accept that there were some risks in doing it in that manner, especially on the thermal side. So again, if you want to extend the mission, you have to accept increasing operations complexity. So I'd like to give an example of what I mean by that. So here's a nice example involving a scientific instrument where sometimes you need to be quite creative in order to work within the operational constraints. So we had an instrument called GRB, gamma ray burst instrument or experiment, and we had to switch off the instrument. But one of the requirements was that we could only switch it off if it didn't cool down too quickly, because that could crack the detectors. So we had to find a way of switching this off so that it would not cool down too quickly or cool down any more than 10 degrees Celsius an hour. But the experiment had a simple on-off heater. So how were we going to do this? We couldn't do this using our time tag commands, the ones that we can store on board, because we just simply would need too many of them, and we have other things we need those time tag commands for. And it would also need perfect ground segment performance. So if you were relying on a command going to switch the heater on or off at a certain time and the uplink or downlink failed, you could have a real problem. So we couldn't use that. So someone came up with the idea of using a onboard program that we had that was intended for a completely different use. This program was actually intended to help the spacecraft maneuver around the sun when in conjunction, so that it wouldn't point directly at the sun. But we found out that we could actually store normal commands in this program and operate those. So we plan to use this program to switch this heater off at increasing intervals to help slow down the cooling rate. So overall, this simple operation of just switching off an instrument, it actually took a couple of months to prepare, 2 whole days of operations, and all of that just to switch off a little heater on an experiment. But it was successful, and they achieved a cooling rate well below the maximum that would have caused problems of just 1.6 degrees an hour. And here we have a nice picture summarizing that of the spacecraft data. Um, so we can see here at the top, we have the orange data on. That's the heater cycling on and off. If you look on the left hand side, you can see on off. So that's how rapidly we were cycling the heater. The the green there's a purple line of data, so that shows you the actual um, temperature decrease of the instrument, and in green is another temperature parameter, but this one only worked to about minus 30 degrees, and then the calibration curve didn't work properly, so we had to work with another parameter. And at the bottom, we have our conjunction program is being scheduled and descheduled several times in order to achieve this. So that was a nice, smart way of achieving this goal. So, what were some other impacts of reduced power as the mission went on and the RTG delivered less power? So, yes, you're getting increased mission risk. The operations are getting more complex. And the mission planning, we had to avoid conflicts in power usage. That was the big difficulty we had. And it got to the point where even one internal instrument or an element in the platform failing could potentially cause a very cold spot on the spacecraft and freeze the fuel. We also had decreased radiation to the surroundings. So the reaction control equipment, so the propulsion subsystem, at some areas of the platform, the temperatures were barely above the freezing point for hydrazine. And eventually, we had to actually consider scenarios where we would, for instance, just allow one side of the spacecraft to freeze, and we would have to accept that the hydrazine would be frozen solid, and hopefully it wouldn't burst the pipes and cause other problems. But we could use the thrusters on the other side of the spacecraft towards the end of the mission. And we were running cold, so we actually got to the point where most units were running below their preferred operational limits, the ones that they were planned for. Switching on and off payload items was non-trivial, as I've just illustrated. And even the thermal configuration got to the point where it was not ideal for scientific objectives because the workarounds were reducing the power and thermal margins. So let's talk about some of the other operational challenges that we faced. And remember, this is quite an old spacecraft, quite a simple design. So we had coarse telemetry. So I've worked on other missions where they have thousands of telemetry parameters, thousands of telecommands to send to the spacecraft. Ulysses was working with just a few hundred of each. And we didn't have much telemetry. And for instance, we didn't have important things telemetered like how much power were we getting from the RTG. So we had to actually, we only had that to a resolution of about 1.8 watts. But when you're using the power, we were actually trying to manage this to about 1/10 of a watt. And many of the units are using fractions of a watt. So this was actually quite tricky. So we had to make indirect and derived telemetry. So as I said, we couldn't measure the RTG output directly. So we had to calculate that on the ground, building it up from what we knew of real data. And also the fuel level. So that's a common problem with spacecraft. It's actually quite difficult to measure how much fuel is left in the fuel tanks. We also had thermal model limitations. So the thermal model of the spacecraft was designed for the prime mission, but they didn't look into any extended mission configurations in the way that I've described. And we very quickly found that there were quite significant differences between the modeled and observed values that we were seeing on the real spacecraft. And Ulysses was a very old, very simple mission, so we didn't have an electronic spacecraft simulator. So we couldn't actually practice any configurations or operations. Our spacecraft simulator was literally getting the operations team and the ground segment team into a room, and we just talk our way through the operations and figure out in real time in our heads if they'd work or not. So fortunately, I don't think that's a problem most missions have nowadays. And some further operational challenges. So because Ulysses kept getting extended, it had lower priority for antenna time with the Deep Space Network. So that reduced the amount of data we could get back. It made the operations get slightly more tricky as we went on. Another important thing to think about is with long duration missions is loss of design knowledge. So Ulysses, because it was designed in the 70s, built in the 80s, not launched until 1990. Many of the people who originally worked on the design or the integration, they very quickly retired and left the project. So, we were on our own. There were no other experts except ourselves. And this is really critical as the spacecraft aged. You get more problems. You need to really dig down into the subsystems. What are the problems? And this was quite a tricky problem. And the science return. So, what we did as an operations team is, we helped facilitate this power sharing agreement with the scientists. And this was really critical. So imagine it's pretty much like a mother bear with her cubs. They're so protective of their experiments. They don't want anything to happen to it. So the very mention of wanting to switch them off or have other experiments on instead of them, you can imagine was quite a prickly subject. So we really had to work closely with the scientists, helping them understand the operational challenges and what we had to do, and helping facilitate that agreement amongst us so we could at least get some science back from the mission and keep operating. And we also had a problem when the second X-band transmitter failed in January 2008. This meant that we couldn't transmit data back at the high data rate anymore and had to rely on S-band transmissions at a lower data rate. And that therefore impacted the science return. So let's talk about, with the beauty of hindsight, and again, thinking of people designing spacecraft, what were some of the mission success factors for Ulysses? So we, as most people do, we tried to operate conservatively. This led to the fact that we had few anomalies and a very high data return. We had an old but very simple and robust and reliable spacecraft. And again, this contributed to the long life of the mission. It meant that we could get several mission extensions and operate for nearly 19 years instead of just 5. We also had quite a low operations team turnover. Some of that was probably because a bunch of us were sent out to work in California. And that was a very nice place to work at JPL, the Jet Propulsion Lab. So no doubt that probably helped keep a few of us there. Like I said, I ended up staying there 13 years instead of 4 months. But that was really good because it meant that the knowledge of how to operate the spacecraft stayed in the team. And that, at the end of the day, is very useful to have. And we also had some great, wonderful science, which I'll talk to you about at the end of the talk. And we had a very good data return. And this meant we had a lot of support from the scientific community. The scientists were getting lots of great data. They were writing lots of papers, getting a lot of attention for the mission, making great discoveries. So they were really enthusiastic about keeping the mission going. And because we'd already studied the poles of the sun at a solar minimum and a maximum, then any further science we could get was a bonus. So when we were looking at keeping the mission going in the 3rd and 4th orbits, people were just glad to get any science at that stage. And they got such a good set of science with the first set of polar passes at the minimum sort of quiet conditions and the maximum more turbulent conditions. They were just happy to get more data. And at the bottom of the screen, this is what we call our telemetry map, our data return map. So here, this is for the first 14 years of the mission. And in purple, we have the real-time telemetry. So there you can see roughly the 10 hours a day pass. We have some periods which are fully purple, where we have full-time coverage. And the green data, that's the bulk of the playback data, where we could play it back at the highest data rate. So you can see there's hardly any white gaps at the top. There were hardly any periods where we lost data. And yeah, the scientists are super happy with getting so much scientific data back from the mission. Okay, so that's the part of the talk about spacecraft operations. So I can take another short break here and answer some more questions if anybody has them.
Okay, I think we did get some questions come in while you were talking, so that's nice. I think.
Can you just ask how many people are watching roughly?
Yes, I think we had a peak of 35 people, so that's good. I think that is nice, and I think the number is about the same. It's fluctuating a little, but yeah. So
yeah. Thanks so much.
So let's maybe take two questions because some of them are quite technically heavy, and I probably want to keep them to the end of the talk, so you have
Okay.
maybe a bit more time to talk about them.
Sounds
But
good.
so for the first question is maybe quite simple. Why is the mission named Ulysses? Is there a reason for the name?
Yeah, so this is to do with the mythical legend of Ulysses going on a long journey and returning, I think, to Ithaca. And this was likened to the long journey that Ulysses, the spacecraft, would have to go, um, and then return to the sun to study it. So I know I had some colleagues who were much better informed about mythology than myself, and they could explain it a lot better. We had some other. I remember when we were trying to make some software tools to help us operate the mission. We managed to even find further references to other mythological, with other mythological links, and keep the theme going. And originally, Ulysses, it was going to be called ISPM, the International Solar Polar Mission, was one of the early names for the mission. But I think Ulysses was a nice and apt name for it.
Okay, yeah, thanks. And the other question is why is there this distance to the sun? So, was there a reason that the specific orbit was picked?
Yeah, great question. So, in the early stages of designing a spacecraft mission, people will do a mission analysis study and they will optimize the orbit. So, whether it be orbiting around the Earth, low Earth orbit, geo, medium Earth orbit, or in this case, an interplanetary orbit, there'll be a lot of work will go into optimizing that orbit. So, I think this would have been planned. At one point, we had to go out to Jupiter, so that's one end of the orbit is fixed, and then they could presumably tweak the way that we passed by Jupiter, and then figure out where we would end up in terms of distance from the sun. And I'm assuming that for the scientists, this gave them a nice balance between distance from the sun and getting a good view of the poles. And they probably didn't want to get too close to the sun because then we would have had thermal problems. So that would have also been a contributing factor. So in the end, yeah, this is the way the mission was designed. I remember before the Jupiter flyby, getting our daily updates from the trajectory people from NASA, and that was fascinating because they were aiming initially for a window. I think it was 1,000 kilometers square. So they're getting their range tracking and ranging data. And they literally put up a graphic of this 1,000 kilometer square and where Ulysses is and the error margins. And then the next target they aim for is, I think it was 100 kilometers square, something like this. So basically, you aim for a big window, smaller window, and then a much tinier window. And then they got a really accurate injection around Jupiter and a really accurate orbit. So that was also really interesting to see that happening from that team.
All right, yeah, thanks. We have more questions, and to those people, we will still get to your questions at the end of the stream. So we have another Q&A session at the very end, because there are quite some interesting questions in the chat,
Oh,
I
great.
think.
Oh, that's fantastic.
But yeah, I think that's only one part of the talk is left about the scientific results,
Yeah.
right? So let's cover that, and then we can enter a more extended Q&A where I will pick up all the questions that are left and maybe some new ones.
Great. Well, the good news is for everyone that this is the shortest part of the talk because I'm not a scientist, so hopefully that will help. So
All right.
They won't have too long to wait.
Yeah. Well then, take it away.
Yeah. Okay. Yeah. Okay. Ulysses Science. By the way, I hope you can see the credit here to a guy called David Hardy. So I can remember when we started getting these wonderful artistic images that he created for the Ulysses mission. So it really helped us to visualize how it may have looked. Okay, let's talk a little bit about Ulysses Science. So we were very fortunate with the science because it was really perfect timing. So if you look at this graphic, I can explain why. So in yellow, we have the smooth sunspot number, and you'll see a green bar and a red bar labeled here for the first solar polar passes, the southern and northern passes. And these were happening very close to a minimum in the solar cycle. So that was great because it gave the scientists an opportunity to get their first set of real science data when the sun was relatively quiet and stable. And that really helped them in understanding what they were seeing at these different latitudes. And as we move along, you'll see that the sunspot number reaches a peak, and the second set of polar passes were shortly after this. So for the second set of passes, we were seeing a much more turbulent and energetic sun, and that gave them a great comparison of the cycle that the sun goes through. So let's talk a little bit more about other aspects that contributed to the science. So I'm showing you a series of graphics here to help understand how the science and operations phased together. So the first graphic here is just showing the range of the spacecraft from the sun in astronomical units. So you can see at the beginning on the left, the quick trajectory out to Jupiter. So we get a very steep increase in the distance, and then the sharp change in direction as we went around Jupiter. And then we get into the cyclical range from the sun as we are fixed in the final orbit. And then beneath this, we see the sunspot number that we had for the mission. And this data was taken, I think, in 2004. So you can see the jagged actual figures and then a prediction for the sunspot number. And at the bottom now here, we have a nice layover of, you'll see at the bottom are the dates. And we are showing here basically the percentage of the payload that was switched on. So you will see a core payload and then the discretionary payload. So as you can see, for most of the mission up until March 2002, we were able to have the full payload switched on, and that meant maximum data return and very happy scientists. And then it was only for the last 6 or 7 years of the mission that we had to reduce the payload. And you'll see as we move along here, as we get to the further distances, you'll see that we have to switch more and more of the payload off in order to operate the whole spacecraft and keep it warm enough. So a fantastic overview of almost 19 years of the mission here, just captured in a few graphs. Solar wind speed. So one of the major things Ulysses wanted to study was the solar wind. So this is the stream of particles coming from the sun, forming our heliosphere, the bubble that we are orbiting around, the influence of the sun in our galaxy here. So this graph is showing in the middle, it's using a picture taken, I think, from SOHO of the sun. So obviously not a picture from Ulysses. And Ulysses, we only had instruments recording values. So you see the wiggly lines, that's the Ulysses data. And what's interesting to see here is that we have two very distinct regions of the solar wind. And this was a new discovery for Ulysses. Nobody realized that the solar wind moves so fast when you got to high latitudes. So on the left, you can see that we have periods around the equator when we have this solar wind speed around 350 kilometers, and then a very sharp increase to the higher level of 750 kilometers per second for the solar wind. And this was repeated on the other side also. So an amazing discovery by the mission. So we had low wind speed at the equator, much higher at the poles, a very rapid transition. And then because we had the solar polar passes taking place at different phases in the solar cycle, we were then able to compare it during the quiet and more noisy phases of the sun. So this was also very interesting for the scientists. So here we have on the left is the previous plot, and on the right you see the much more noisy and disturbed solar wind speed superimposed around the picture of the sun. So very different results and very, very interesting for the scientists to look at and study in depth. Before Ulysses, the sun's magnetic field was thought to be somewhat similar to the Earth's. So you have the magnetic field and it's concentrated at the poles. So that was the model that we had. But with Ulysses, we had much better data, and we actually discovered that the sun has a much more uniform magnetic field. So yeah, a lot of scientific theories had to be ripped up, and the models had to be updated as a result of these Ulysses findings. We also helped to discover and find out information about magnetars. So, magnetars are sort of the magnetic equivalent of a pulsar. And these Ulysses measurements, so they're plotted as what's called a light curve. And we see in a very short time period a very intense flash of radiation, followed by a gradual decline in the gamma rays that were measured from this source. And this was an amazing discovery by Ulysses, and it actually became the classic light curve for these highly magnetized stars. And another very interesting point, I remember when we looked at our telemetry map for when this short period of data was recorded. So you see here maybe 50 minutes of data. And if I recall correctly, I think we observed that we had a data gap very close to when this data was recorded. And this is really important because we put an awful lot of effort, the whole team, the spacecraft, but also the ground segment team, in recovering every little bit of scientific data that we could. And this scientific discovery really drove home to us that you could just miss a few minutes of data and you would literally miss a scientific discovery. So this is a great motivator for the team. This was from an American instrument, so this was from the University of California in Berkeley. By the principal investigator was Kevin Hurley. And so that was some expected science, and we also had some very interesting unexpected science. So here we have a lovely image of Ulysses and a comet going around the sun. And we unexpectedly encountered the tail of the comet Hyakutake in 1996. This was an amazing comet. I remember seeing it. And nearly 4 years later, someone looking at the data again was able to realize that we'd actually gone through the tail of this comet. And this was quite an astounding discovery because when they did the calculations, they figured out that this comet tail was over 500 million kilometers long. It was actually the longest one ever recorded. And it's a wonderful story, this, because this was I think it was a young postgrad, was given some old data to look at. So the principal investigators had already looked at this data. They thought they got all the science out of it. But this postgrad, this postdoc, he looked at the data and noticed something that was a bit strange about the readings. And he did some investigations, and he contacted us and others and checked what could be causing these bumps in the data. And this was the explanation he came up with. It was the only thing it could be. So I think it's a wonderful story for people that, never assume if you're given a task that it's not going to be exciting or there couldn't be something in there just because somebody's looked at it before. And this young scientist was suddenly catapulted from being a postdoc to literally being a science star, getting lots of media attention and becoming very important. And I can actually tell you that nowadays he is leading up a very exciting mission for ESA called Comet Interceptor, which is being planned at this moment. So a wonderful story how carefully checking old data can actually bear amazing results. And we were also able to detect other comet tails later in the mission as well. Here we are in February 2004, comet Mignaud-Hartley. So fantastic additional science that we didn't expect. Another piece of science that Ulysses was designed to study is called the interstellar helium flow. So apparently there is interstellar helium flowing into our solar system, and several different spacecraft have tried to get some measurements on this and try and identify its speed and roughly where it is in the heliosphere. And Ulysses was able to contribute to these measurements as well. And we were able to help verify that other readings were, pretty good and help add to that data set. And we also had a very interesting instrument, which actually was trying to collect dust in the heliosphere. So this was called the dust instrument, and it was from an institution in Germany. And here we see a plot of some dust streams coming from one of the moons of Jupiter called Io. And you can see on the plot, we have the impact rate of small dust particles that are recorded by the instrument. And you can see these have a cyclical pattern. We have 8 strong peaks occurring. This is the cluster, the second cluster of red peaks that you see after June 2003. So these apparently were caused by some dust storms on Jupiter, and Ulysses was finding these from very far away. And then we have another peak in late November 2002, so just before the gray bar. That was also another distant dust stream from Jupiter, the most distant one ever detected. So again, incredible numbers. This is 3.3 astronomical units away from Jupiter, and we're detecting tiny bits of dust. And the blue little lines you see at the top of the graphic, they're indicating the rotation period of the sun. Okay, so that's a few of the scientific highlights of Ulysses. And just a quick wrap up then, some summary and conclusions about the Ulysses mission. By mid 2004, our unique trajectory and amazing science was really producing some prodigious results. So we already produced more than 60 doctoral theses, and several thousand refereed papers have been written by the Ulysses mission. And that's continuing until today as well. Even though it finished in 2009, there are still occasional papers being published using Ulysses data. So it's really been a successful scientific mission. And again, going back to my technical discipline, the conservative spacecraft operations, this increasing, this acceptance of increasing risk in the mission, that helped us achieve mission extensions together with the scientists. And we were able to provide valuable and new and interesting science with reducing resources right until the end of the mission. So at the end, we completed almost 19 years, 6,842 days of continuous science operations instead of just 5 years. So really an amazing achievement. And I've put at the bottom here some links. So I hope these are still operating. You can imagine that some links are no longer maintained, but the last time I checked in, these links were still operational. And if you're interested, you can get lots more information about the mission. And there's even a data archive, which has been set up by ESA. And yeah, you can get a feeling for the scientific data there. So that brings us to the end of my talk. And I think Igor said that we have some more questions. So hopefully I can help answer those.
Yes. So, yeah, once again, thank you for the talk. It was really informative. It is kind of crazy to think about the fact that it's been, 19 years, which is a very long time for something that you just launch in space and hope it works. But okay, so we have quite a few, I think, quite interesting questions. We are approaching the end of the, I guess, schedule that we had for it, but I think it's fine if we go a bit over time. So let's just, keep the time still a bit in mind. Okay, so our first question is from Sebastian. If you were to redo the mission right now, what would you change in the mission design and the profile compared to last time?
Okay, nice question. So I think I've probably already highlighted a few things would be nice to change. So I think we'd have a much more sophisticated spacecraft. So we'd have a much more flexible operations because you could do so many more commands. You'd have much better telemetry. You could operate it more easily. And we'd have solid state recorders. You could record the data much more easily. Perhaps you could do all of these operations in very short tracks, cost less money. A camera would be nice, of course, because then you get wonderful images, and they really make a difference when people are trying to do outreach as well. That makes such a difference. So those, I think, would be a few of the things that we could do. And maybe this time they could use solar arrays instead of a nuclear generator, and then you could have a lot more power. That would make a huge difference to what you could do. Good question.
Okay, yeah, well, that's a nice insight. Thanks. The next question is coming from Michelle. She asks, how does the infrastructure built in the spacecraft reduce the effect of radiation from the sun?
Okay, radiation from the sun. That's a good question. Maybe if I answer this indirectly, I think the toughest radiation environment we had was when we were passing Jupiter. So I think that was the radiation critical moment. So I mentioned about one of the onboard computers having a corruption after we passed by Jupiter. I remember when we were doing the anomaly investigation, the manufacturers described how they had built radiation hardened components. So they'd put extra layers of protection to hopefully prevent any radiation penetrating and affecting the silicon wafers, really the silicon components. So I think rather than the sun, the limiting factor there is going around Jupiter. And I know from seeing other presentations about mission designs to Jupiter, radiation is a massive mission limiting factor. That's what will really stop the mission working, is components being, yeah, just literally getting destroyed.
Okay, yeah, I guess it is a bit counterintuitive that Jupiter has more radiation than the sun, but yeah, thanks for the answer. So next question is, what did actually cause the spacecraft to fail in 2009?
So it wasn't failure so much as we got to the point where it was just impossible to operate any longer. So I think, if I recall, I've read some of the logs and press releases about it. So at that point, the spacecraft was moving away from the sun again, and so we were getting into the problem again of having enough heat to keep the spacecraft warm. And I can only assume it was getting to the point where you had to switch all of the payload off in order to keep the spacecraft alive. And at that point, it's not worth running anymore. I remember trying to think of a way to keep the spacecraft pointing at Earth while it was in this phase, so you could potentially switch it off, get people to try and contact it, and have it. It would have a special mode that would keep it pointing at Earth while it was going around this phase. But it's not something we were able to study and implement. And then the idea would have been when it came back again another time and it was warm again, you could have maybe switched it on again and had some limited science. But yeah, we'd done 3.5 orbits by then, so yeah, it was really it's the diminishing returns problem. There are other missions that are more worthy of spending money on at that point.
Okay, and I think maybe a follow up to this. Why not use solar energy on a satellite if you want to prolong the mission?
Yeah, well, this is something that is possible now. So we have a mission at the moment being designed called JUICE, Jupiter Icy Moons Explorer, and that's got some massive solar arrays. So solar array technology has really progressed a lot in the last, remember, 50 years we're talking about here. So we've got silicon and is it gallium arsenide solar arrays. So they're more efficient. We have solar concentrators that actually reflect more light onto them to again increase the level of power that you get, and we can make them bigger. And the trouble is that when Ulysses was designed, they just simply couldn't make big enough arrays. Or if they did, they'd be so big you couldn't launch it, or it would be so complicated to operate, it couldn't do the science. Remember again that Ulysses is a spinning spacecraft, so that could also be an issue with solar arrays, that you're having it spin, and then you've got these solar arrays sticking out around the mission, around the axes of the spacecraft. Maybe that's also not a very good configuration. But good question. As I said earlier, that could be perhaps something that could be looked at if it was to be tried again.
Okay, so good. Yeah, I think it is a bit also hard to think about the fact that indeed you said that you worked with 70s technology. So indeed there's a quite big design gap. We have a question from Danny. So after the Challenger disaster, some planned payloads ultimately launched unmanned. And the question is, was there an alternative launch vehicle planned if it couldn't make it on the shuttle? So maybe a Delta booster or something like that?
I don't know if that was ever looked at. I suspect that because we needed these two large upper stages, the only vehicle that could take us there was the shuttle. But I don't know that for sure, I must admit. So I can't answer that completely. But I suspect the shuttle was the only way that we could get enough upper stages up there to boost it in the fast trajectory to Jupiter.
Okay. So the next question is from Carl. So how do you think 5G will contribute to the telecommunications between missions like Ulysses in the future and the NASA on Earth?
Oh gosh, that's a good question. I'm not familiar enough with 5G to directly answer that. Maybe I can answer in a roundabout way. We've got Ulysses is a mission that transmitted its data at X and S band. I know that the Deep Space Network has upgraded its systems to include K band and Ka band. But I must admit, I don't know what that means in relation to 5G. I think 5G is more a telecommunications protocol. But I honestly, I don't know enough about it to answer that. I'm sorry.
Yeah, I think maybe the question was about the fact that it's a new frequency, so maybe
Oh,
that would introduce some error.
yeah.
But
I think I have a feeling that for this kind of mission at these extreme ranges, you have to use something like X band because you need a very focused beam with enough power, and that's the best one to use. The trade-off is that, if I remember correctly, X band is more susceptible to weather, so S band is better in that sense, but it's only effective at shorter ranges. So when we lost the X band transmitters, we could only broadcast out to a certain range. And actually, thinking back to the earlier question about why did the mission end, they'd lost both X band transmitters by that stage, so that's probably another contributing factor was losing data as they got further away at S band.
And we have actually one more, maybe a rocket-based question.
Oh yeah.
So Ulysses was initially planned to be the first to use the center G prime stage.
Oh, okay.
Unfortunately, the shuttle center never made it. So what had to be changed to make the adaptation to the IUS? And a secondary question, what other technical improvements had to be made in the gap between 1886 and well, I mean, sorry, 1996
Yeah.
and 1990?
Um, yeah, I'm not that familiar with this aspect of the mission, I must admit, but I do recall reading something about the upper stages having to be changed. Um, Now, I have a feeling that the upper stages Ulysses used were both solid fuel, and maybe the Centaur was liquid fueled, and that turned out to be too dangerous for the shuttle crews. They didn't like the idea of using that, so that was probably that factor. And then going to the second question about what changes happened between 1986 and 90, actually, I think very little because once the Challenger disaster happened, they literally put Ulysses into hibernation. They locked it up, sealed it up in a box, a large white box, and kept it in obviously controlled storage, not knowing when or if the mission could actually happen. So they just had to put it in a box very carefully, hermetically seal it, keep it somewhere safe until they could figure out when it could be launched again. So as I understand it, they locked it up, and then when the new mission was confirmed in 1990, then they opened the box and they went through another testing campaign to make sure that nothing had gone wrong while it was in storage.
Okay, well, that's
Yeah, good question.
yeah, that's a good question. And actually, perhaps a question from me as
Yeah.
well. So you were with the mission for quite a long time, and I'm sure you had a lot of different experiences with it.
Mhm.
So what for you was maybe the best, most exciting moment out of the experience of operating the mission?
Well, I went originally for the Jupiter flyby, and Ulysses got an awful lot of media coverage then. I remember the weather was absolutely atrocious. So in California, you often get really bad rainstorms in the January, February, March months. So we were working around the clock. I think I was probably in the night shift. Um, but I remember the media crews coming in. We had all the dignitaries from NASA and ESA visiting. So that was really exciting seeing people coming to see our little mission. And we all counted down the time until we got to the Jupiter closest approach, keeping your fingers crossed that you would keep getting telemetry data to show that the spacecraft was alive and had survived the intense radiation environment. So that was really exciting times. So yeah, that was certainly one of the highlights. And then I remember the nutation operations was something I helped do a lot of the planning and testing for. So I can remember maybe the first operations that you've planned yourself, and you're authorizing commands that you've specifically come up with, and some overall test. And you're a young engineer, so you're thinking, I got to get this right. And it's very reassuring when you see the data coming back and you're able to report the next morning, the test went fine. This is what we saw. Look here, you can see the different levels happening. This proves that this is happening on board the spacecraft as we expected. So yeah, that's one of the joys of spacecraft ops is you're ultimately deciding which commands get sent to the spacecraft when, and then you get to see that happening. On an Earth observing spacecraft, it's happening in a few seconds. On our mission, that could be taking almost a couple of hours to happen. So you're waiting, sitting, waiting, keeping your fingers crossed that everything's going to work out.
Yeah, I can imagine it is quite exciting, and I think, indeed, seeing that data come back must feel really good. It feels very good on Earth, so I think when you get something back from a thing in space very far away, it feels probably even better. But I think this was pretty much it in regards with the question that we had. So I think we actually even managed to fit in our time frame, which is very nice. So from my side, I would once again like to thank you for staying with us on this Friday evening. I really like to talk. I think people watching us also quite enjoyed it. We saw some really interesting questions about the technical side of it. And it was definitely interesting hearing a perspective from satellite operations. And I don't think you hear that too often in your everyday life.
Yeah. If you just switch back to the presentation for a moment.
Yes, it's still visible.
It is, okay. No, I was just, thanks everyone for spending some of your Friday evening listening to me. I really, really appreciate it. Some great questions, so thank you for those. And I've put up my link for LinkedIn, so please feel free to connect with me on LinkedIn, and you can have a look at my space career and get in touch if you have any other questions. Be happy to hear from you. And for the students, enjoy your studies. I'm very jealous. I think Igor was telling me you're making rockets at the University of Twente. And
we're trying to.
Trying to. Fantastic. Go. Failure is an option, so break stuff. That's how you will learn. You're so lucky to be studying, and you've got all these facilities. So make the most of it, and enjoy your career, hopefully in the space industry.
Thank you for the nice words, Andy. And for everybody still watching the stream, thank you for sticking with us. If you want to follow us, the Space Society Twente, you can, of course, look in the description for the links to our social media below. Please contact Andy on LinkedIn. I'm sure he'll be also happy to have you in his network. And have a nice rest of your evening, and have a great weekend, everybody.
Yeah. Thanks a lot, everyone.